Hello everyone, this is a new video on extra topics for this course. One of you asked me to justify linearization and our use of Taylor series a bit more thoroughly. So this is the topic of this new video. We first will have a look at Taylor series and then look at linearization and look at when it works and when it doesn't. So let's first look at the Taylor remainder theorem. We have a function that we assume is smooth enough on an interval, and the interval is centered around x0 and either goes like plus h in one direction or minus h in the other one. But as long as we have included enough space, we want our function to be smooth enough in the sector we're looking at. So we're looking at the sector that starts at the x0, that is the point we have the most information about, and moves away in either of the two directions. We say that it moves away by h. That can be positive or negative. So it's either moving on the right if it's positive or on the left if it's negative. Then we can write the value of the function at f(x0 plus h) with a sum of information about the derivatives of f at x0. We can either truncate after a certain number of terms or add the remainder. If we add the remainder, actually it's an equality. It's not an approximation anymore. So the first terms in here are the standard Taylor series. So fx0 plus f prime x0 times h plus 1 over 2 factorial second derivative of f at x0 times h squared, and we keep on adding this nth derivative of f, all computed as x0, divided n factorial times the distance time at the power a, and the residual. The residual is the part we are interested in this theorem. It states that the difference between the truncated Taylor series at order n has actually a form that we can study. It depends on the distance from the point you're taking all the derivatives at power n plus 1 times the nth plus 1 derivative at the point xi. We don't know the point xi, but we know it is between x0 and x0 plus h. So as long as we are controlling or having some information on the next derivative of f on a full interval that we're looking at, we're good. We know how the function changes with an approximation, and we know the worst error that we can make. Let's look at an intuition. I know the drawing is not great. There is going to be a better one the next slide. So we have this blue function and a point that we can start approximating by a line, then that is tangent to the function. Then we can try approximating with a parabola, then with a third order polynomial, then a fourth order, and so forth. So we're trying to approximate our function with polynomial information through the derivatives. So the more derivatives we have, the better approximation we're building up. The worst error is of the shape that we have seen, where xi ends up being the worst point, that is the place with the highest n plus 1th derivative in the interval. And that depends on the distance itself. So the further away we are, the worse this coefficient h at the n plus 1 is. But if we're very close to x0, that coefficient is pretty much 0, and at the power n plus 1 is even smaller. So here is a picture to show the Taylor approximations of the sine starting at 0. So the first approximation you see is just a tangent line. The second approximation is a parabola that goes straight down. The third is the yellow. It has two squiggles, and it's already better than the previous one, the orange one. Then we have the purple that goes down, the green, the light blue, the dark blue, and each one gives us a slightly better approximation than the previous one. So each one allows us to have more information on the sine further away from the point 0 that we started at. Sine is an analytic function. That means that if we have an infinite Taylor series, then we can approximate then we have the precise value of the sign for an interval around the point in which we computed the derivatives. Sine is even better. Sine is analytic everywhere. That means that if you have the infinite Taylor series, doesn't matter where you computed it, you retrieve the sine over the whole real axis. So let's go to the second part of this video, linearization with Taylor series. So around the point x0 that we have chosen, we can say that f of x can be approximated by f computed as x0 plus a linearization. So the first derivative computed at x0 times the distance between x and x0, where the error is bounded by this remainder theorem. So second derivative of f computed xi, where xi is between x and x0, divided by 2 times x minus x0 squared. Let's look at this term a little bit. Let's say that xi is fixed. Then this term gets smaller the closer we're getting to x0. So if we are at x0, this term is 0, and the further away we get from x0, the worse it gets. It also gets worse because xi can get to have even worse values. But if our remainder is much smaller than our approximation, then looking at the approximation, so at the linearization, we have enough information to usually do what we want. Look at the fact that both terms in this inequality depend on x minus x0. The one on the left, on the right, our linearization depends on x minus x0 just linearly, our remainder quadratically. So if we are decreasing x minus x0 enough, then our quadratic term, the remainder, will become much smaller than our linearization term. So the problem is not, if everything goes right, if the linearization is reasonable or not, but how close to x0 do you have to be in order for the linearization to be reasonable? Let's look at some cases in which the linearization is not trustworthy. One case is when f of x0 is 0 and the first derivative is 0. Then the remainder of the Taylor remainder theorem is the only thing that is determining f. Let's make an example. Let's define f of x as x squared times gx. We are studying at x0 equal to 0, and we know that g0 is different than 0. But the value of f at 0 is 0, and the value of the derivative of f at 0 is also 0. The linearization would just say that f of x is equal to 0. But this is a pretty poor approximation, especially if g of x is interesting. So we're definitely not doing a good job. By the way, g of x in this case could just be the constant. What is another case in which linearizations are not trustworthy? When we're looking for very precise answers. That might be a bit confusing, so let's make a precise example that we have seen in our topic, in our course up to now. Centers in autonomous ODE systems. So we have studied how we can take autonomous 2D ODE systems and study their equilibria by studying the linearization next to the equilibria. And I've always been fairly careful pointing out that that is a study of the linearization of the ODE. One case in which this linearization is often wrong, not always, but often wrong, is when we retrieve centers. We retrieve centers when the eigenvalues of the constant coefficient matrix associated to the linearization of the ODE system has purely imaginary eigenvalues. That means that the real part of the eigenvalues of the matrix is exactly 0. No approximation in there. It has to be exactly 0. This is something a bit too much to ask when you're looking at linearizations of more complex problems. So Here is a sketch. X prime equals to minus y prime equals to x, has a periodic solution, as only periodic solutions, as the sine-cosine problem. But if you add a second order term, then suddenly you lose the periodicity. But the linearization is still the same. It's just that we are asking the linearization to give us something exact, while the linearization can only give us an approximation.